You know those long, kind of scary-looking chemical names? What if I told you they're not scary at all? They're actually just a set of simple instructions. Today, we're going to demystify the system for naming chemical compounds. And I promise by the end of this, you'll see it's all about logic, not just memorizing crazy words. Let's jump in. So, here's the key. The secret to understanding all this is to stop thinking of a chemical name as a random word and start seeing it for what it really is, a complete address. Yep, every single part of the name tells you exactly where an atom is and what the whole molecule looks like. All we have to do is learn how to read the map. And here's our map for today. First, we'll take a chemical's full address and pull it apart. Then we'll get into the 5 universal parts that make up every name. After that, we'll build a molecule's carbon skeleton, add on all the extra bits and pieces, and by the end, you'll be able to decode any chemical name you come across. Okay, let's get right to it. First up, deconstructing a chemical's full address. You know, sometimes the best way to figure out how something works is to just take it apart. So let's grab a name and see what's inside. Okay, check this out. 3-chlorobutane-1-ol. I know, it looks like one long, intimidating word, but trust me, it's not. It's a code, a set of instructions, and we're about to crack it together. Let's use our address analogy here. The 3-chloro part, that's like a decoration on the outside of house number 3. The middle part, boot, that's our street name. It tells us the main chain has 4 carbons. Then we've got an, which is like the type of road. In this case, a paved road with all single bonds. And finally, 1-ol tells us there's a really special feature, an alcohol group at house number 1. See? Each piece has a job. So taking that name apart shows us a pattern. And what's cool is that every single chemical name in this system is built from the exact same 5 components. It's like a universal blueprint. Let's check it out. And here they are. It's actually a lot like reading a sentence from left to right. We start with prefixes, which tell us about any branches or if it's a ring. Then comes the word root. This is the heart of the name, telling us how long the main carbon chain is. And finally, the suffixes at the end describe the bonds and the most important group on the molecule. Every single name follows this order. All right, section 3. Let's zoom in on the absolute foundation of the molecule, its carbon skeleton. This whole thing is built from just 2 of those 5 parts we just saw. The word root for the length, and the primary suffix for the type of bonds holding it together. So, the word root is the first bit of vocabulary we need to learn. It's super simple. As you can see, 1 carbon is meth, 2 is F, 3 is prop, and so on. This is basically the street name in our molecule's address. Remember our first example? The but told us we were on a 4-carbon street. Next up, we use the primary suffix to describe the road itself. If all the carbons are linked by single bonds, it's an ane. If you spot a double bond, it becomes an ene. And if there's a triple bond, it's an ine. That's how we know if our 4-carbon street is butene, butene, or butine. Easy, right? Okay, quick pause. Before we add anything else, we have to talk about the single most important rule in all of chemical naming, the lowest number rule. It's this simple. You always number the carbon chain starting from the end that gives any special features, like branches or double bonds, the lowest possible number. In chemistry, just like in real estate, it really is all about location, location, location. Okay, moving on to section 4. So we've built our basic street, the carbon skeleton. Now it's time to add all the interesting details, the decorations, the side streets, the things that make each molecule unique. And we do that with our prefixes and suffixes. When you've got branches, there are 3 key rules. First, the longest chain rule. You got to find the main street, the longest possible path of carbons. Second, the lowest locant rule, which is just our lowest number rule applied to branches. But what if you have a tie? What if numbering from either direction gives you the same set of numbers? Well, that's where our 3rd rule, alphabetical order, steps in to be the tiebreaker. So let's think about that exact situation. Imagine you've got a chain, and numbering from the left gives you branches at carbons 3 and 4. But numbering from the right also gives you 3 and 4. It's a dead tie. So how does this alphabetical rule actually save the day? It's beautifully simple. The alphabet decides for us. If our 2 branches are an ethyl group and a methyl group, we just look at the letters. Since E for ethyl comes before M for methyl in the alphabet, the ethyl group gets the lower address number. So the correct name is 3-ethyl-4-methyl-hexane. That's it. And finally, the last piece we add is the molecule's most important feature. which we identify with the secondary suffix. These are called functional groups, and they really give a chemical its personality. For instance, as you can see here, an OH group makes it an alcohol, and we use the suffix -ol. A carbon double bonded to an oxygen gives us a ketone, so we use the suffix -one. This is the grand finale of the name. And that brings us to our last section, putting it all together. We've collected all the tools, we know the 5 components, we've learned the vocabulary, and we've got the rules down. So let's build a complete chemical name from scratch. All right, here's our challenge. We've got a molecule with a 6-carbon chain. It has a double bond that starts at carbon number 2, and it has a little 1-carbon branch sticking off of carbon number 4. Let's figure out its full proper chemical address. Let's do this step by step, just like on an assembly line. First, the word root. 6 carbons? That's hex. Okay. Next, the bond type. We've got a double bond, so that gives us the suffix -ene. Where is it? It starts at carbon 2, so that piece is 2-ene. Now for the branch. It's a 1-carbon group, so we call that methyl. And its address is carbon 4, which makes it 4-methyl. We've got all our parts. Now we just assemble the pieces in the right order. Prefix first, then the root, then the suffix. And what do we get? 4-methyl-hex-2-ene. Boom! Every single piece of information we started with is perfectly encoded right there in the name. We've built the address. And that's really the whole secret. It isn't some kind of magic. We just used those 5 core components to turn a complicated-looking structure into a perfectly logical name. It's a system. So if you take one thing away from this, let it be this. Chemical names aren't scary words that you have to memorize. They're part of a logical, systematic language. Once you know the 5 basic parts and a few simple rules, you can read and write the language of chemistry. Which leaves me with one final thought for you. We just broke down the universal language of chemistry. But what other kinds of universal languages are out there that help us describe our world? You know, things like mathematics or musical notation or even computer code. What other systems do we humans create to bring order to all the complexity around us? Something to think about. Thanks for joining me.